Hi everyone. Today, we embark on a journey into the fascinating world of molecular chemistry as we explore Huckel's rule and its impact on aromatic compounds. Welcome to the presentation on Huckel's rule in molecular chemistry, understanding aromaticity in molecules. So let's begin. Imagine a world within molecules, where a subtle dance of electrons determines the essence of their stability and reactivity. In this captivating realm, we encounter Huckel's rule, a guiding light in the intricate tapestry of organic chemistry. Conceived by Erich Hückel in the 1930s. This rule serves as a linguistic bridge between the language of mathematics and the aromaticity of compounds. The formula 4n plus 2 equals pi electrons, akin to a secret code that unlocks the secrets of aromatic molecules. It is this code that whispers tales of stability and resonance, revealing the hidden elegance within molecular structures. As we delve into the mathematical poetry of Huckel's rule, we embark on a journey to decode the language of atoms and electrons, a journey that promises to unveil the beauty and significance nestled within the heart of organic compounds. As we delve into the core of organic chemistry, aromaticity emerges as a pivotal concept. Aromatic compounds play a crucial role in the stability and reactivity of molecules. Huckel's rule, a mathematical guide, stands as our beacon in understanding and predicting aromaticity. Aromaticity is a crucial concept in organic chemistry, influencing the stability and reactivity of molecules. This property of the conjugated cycloalkenes enhances the stability of a molecule due to the delocalization of electrons present in the pi-pi orbitals. If the molecule obeys Huckel's law, the stability of that molecule is very high compared to others. The heart of Huckel's rule lies in its formula is 4n plus 2 equals pi electrons. This mathematical expression serves as a compass, guiding us to determine whether a molecule possesses an aromatic character. Let's unravel the significance of this formula in our exploration. So, according to Huckel's rule, we can categorize all the organic molecules into three groups. 1. Aromatic molecules, 2. Antiaromatic molecules, and 3. Non-aromatic molecules. Let's see how the molecules behave. 1. Aromatic compounds. 4n plus 2 equals pi electrons. Aromatic compounds have a conjugated system of electrons, and the total number of pi electrons follows the formula 4n plus 2. Examples: benzene, pyridine, naphthalene. 2. Antiaromatic compounds. 4n equals pi electrons. Antiaromatic compounds also have a conjugated system of electrons, but the total number of pi electrons follows the formula 4n. Examples: cyclobutadiene, cyclopentadiene, in its open form. 3. Non-aromatic compounds. 4n minus 2 equals pi electrons. Does not follow Huckel's rule. Non-aromatic compounds do not satisfy the conditions specified by Huckel's rule. Examples: saturated hydrocarbons, alkanes, tetrahydrofuran. Conditions for aromaticity. To qualify as aromatic, a molecule must meet specific conditions. These include a planar structure and a continuous loop of conjugated pi electrons. Conjugated pi bonds means you can see a pi bond next to another single bond in an alternative pattern. Examples of aromatic molecules. Let's bring theory to life by exploring examples of aromatic molecules that adhere to Huckel's rule. From the timeless benzene to the intricate pyrrole, each exemplifies the beauty of aromaticity. Join me on a visual journey through these molecules. Benzene, pyridine, naphthalene, anthracene, pyrrole. Let's check how these molecules are considered aromatic molecules according to Huckel's rule. First, benzene. As you can see in the picture at the bottom, it shows benzene. It has a cyclic structure with 6 carbon atoms and 3 double bonds. So, it contains 6 pi electrons, which means 3 double bonds. The formula 4n plus 2 equals pi is applicable here. N, we called it an integer. Then benzene, n equals 1, and 4n plus 2 is equal to 6 and is equal to the number of pi electrons. Therefore, benzene follows Huckel's rule for aromatic compounds. Let's move on to another example. Naphthalene. Naphthalene has a fused ring structure with 10 carbon atoms and 5 double bonds. It contains 10 pi electrons, which means 5 double bonds. The formula 4n plus 2 equals pi is obeying. For naphthalene, n equals 2, and 4n plus 2 is equal to 10 is equal to the number of pi electrons. Naphthalene follows Huckel's rule for aromatic compounds. Next, pyridine. Pyridine has a cyclic structure with 5 carbon atoms and 1 nitrogen atom. It contains 6 pi electrons, which are 2 double bonds and 1 lone pair. The formula 4n plus 2 equals pi is applicable here, and for pyridine, n equals 1, and 4n plus 2 is equal to 6 is equal to the number of pi electrons. Pyridine follows Huckel's rule for aromatic compounds. As discussed, each of these examples are from different types of proofs with not only pi bonds, but also long pairs. So while doing these processes to find the aromaticity of a molecule, be focused on every part that can form a pi bond. You can see the molecular figures here too. Non-aromatic and antiaromatic. Aromaticity isn't universal. Not all molecules qualify. Some are non-aromatic, and others, intriguingly, are antiaromatic. Understanding these distinctions is key to predicting molecular behavior. Let's demystify the differences together. Non-aromatic molecules as first. Saturated hydrocarbons, alkanes. Alkanes have only single bonds and do not have a conjugated pi electron system. They do not follow Huckel's rule. X, methane, ethane. Secondly, tetrahydrofuran. Tetrahydrofuran has 4 pi electrons, which have 2 double bonds, but is not considered aromatic as it doesn't satisfy 4n plus 2. Antiaromatic molecules. Let's go through examples to find the rule's obedience. First, cyclobutadiene. You can see in the figure, cyclobutadiene has a cyclic structure with 2 double bonds. It contains 4 pi electrons, which means 2 double bonds. The formula 4n equals pi is applicable here, and cyclobutadiene, n equals 1, and 4n equals 4 is equal to the number of pi electrons. Cyclobutadiene follows Huckel's rule for antiaromatic compounds. Next, cyclopentadiene, in its open form, dash. The open form of cyclopentadiene has a cyclic structure with 3 double bonds. It contains 6 pi electrons, which means 3 double bonds. The formula 4n equals pi is applicable here, and cyclopentadiene, n equals 1, and 4n equals 4 is less than the number of pi electrons, 6. Cyclopentadiene, in its open form, follows Huckel's rule for antiaromatic compounds. I think now you have an idea of how to find whether the molecular structure is anaromatic or not. Practical applications. Now, let's shift our focus to the real-world applications of Huckel's rule. Its influence extends across various fields, from drug design and materials science to chemical synthesis. Discover how this fundamental concept shapes our everyday lives. Spectroscopy techniques. As we journey deeper, we encounter experimental techniques such as UV-vis spectroscopy and NMR spectroscopy. These methods confirm the aromatic nature of molecules based on Huckel's rule. Join me as we explore the science behind the spectra. Current research. Beyond the established principles. Current research explores new applications and extensions of Huckel's rule. Researchers continue to uncover novel aromatic molecules, each with its own unique properties. Challenges and limitations. As with any scientific concept, Huckel's rule is not without its challenges and limitations. Complex molecules may not conform to the simple 4n plus 2 rule, necessitating advanced computational methods. Conclusion. In conclusion, Huckel's rule stands as a valuable tool, illuminating the intricate world of aromaticity in organic molecules. Our journey today has uncovered the applications that span scientific disciplines, contributing to the ongoing advancements in chemistry. A property of the conjugated cycloalkenes that enhances the stability of a molecule due to the delocalization of electrons present in the pi orbitals. Aromatic molecules are said to be very stable, and they do not break so easily and also react with other types of substances less due to their stability. But with more conditions, it enhances the reaction speed. Before ending, I will summarize the most valuable points to keep in mind. 1. Aromatic compounds 4n plus 2 equals pi electrons more stable. 2. Antiaromatic compounds 4n equals pi electrons compared to aromatic anti have less stability but considerable stability. Both aromatic and antiaromatic molecules obey the Huckel's rule. 3. Non-aromatic compounds 4n 2 equals pi electrons less stable and does not follow Huckel's rule. Thank you for joining me on this exploration.
Don't forget to subscribe to my channel. Thumbs up, leave a message with your difficult questions in the comment section below. And see you next time with more organic chemistry videos. Bye bye.